December 16th, 1944. The frozen forests of the Ardennes. Technical Sergeant Robert Pearson of the 456th Anti-Aircraft Artillery Battalion stood behind his 90mm gun, watching the grey Belgian sky with trained vigilance. His crew had been assigned to protect the crossroads at Malmedy, a junction the brass considered vital to supply lines threading through the snow-covered hills. What Pearson didn't know, what he couldn't know, was that his gun crew possessed a technological advantage so profound that German Luftwaffe intelligence would spend the remainder of the war desperately trying to understand why their aircraft were dying at impossible rates. The morning was bitterly cold, -15 degrees Celsius, the kind of cold that made metal burn skin on contact. Pearson's gun crew wore every layer they possessed: wool uniforms under canvas parkas, gloves with the trigger fingers cut away. They had been in position for 3 days, part of the sprawling defensive network meant to hold against what would become Hitler's final gamble in the West. The Ardennes offensive, later called the Battle of the Bulge, would rage for 6 weeks and consume the lives of 19,000 American soldiers. But on this particular morning, Pearson's war was about to become something different, something the enemy would never fully comprehend. At 09:45 hours, the distinctive sound of aircraft engines cut through the winter silence. Pearson's spotter called out contacts, 6 aircraft approaching from the northeast at approximately 12,000 feet. Messerschmitts Bf-109s, the Luftwaffe's most numerous fighter. Standard doctrine called for the gun crew to calculate altitude, speed, and trajectory, then fire shells timed to explode at the estimated position where aircraft and shrapnel would meet. It was mathematical prediction, requiring skill, experience, and substantial luck. Gunners fired into empty air, hoping their calculations matched reality seconds later. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But Pearson's shells didn't require mathematical prediction. Each projectile contained a secret so valuable that its very existence was classified higher than most battle plans. The Mark 53 proximity fuse, called VT for variable time, though that designation was deliberate misdirection. The fuse didn't measure time at all. It measured distance using miniaturized radio components that would have seemed impossible just 3 years earlier. Each shell broadcast a radio signal and listened for its own echo. When that echo indicated the shell had closed to within 70 feet of a solid object, a tiny vacuum tube circuit triggered detonation. The shell didn't need to hit the aircraft. It simply needed to get close. Pearson's crew fired 17 rounds in 43 seconds. Standard mechanical time Fuzes might have scored 1 hit from such a barrage, possibly 2 if the crew was exceptionally skilled and fortune smiled. Instead, 4 German fighters fell from the sky in rapid succession, their pilots killed by shrapnel bursts that appeared to anticipate their exact positions. The remaining 2 aircraft broke formation, diving desperately away from an enemy that seemed to possess supernatural accuracy. One pilot, Oberleutnant Franz Stigler of Jagdgeschwader 27, survived the encounter. His combat report, discovered in Luftwaffe archives decades later, described the American anti-aircraft fire as impossibly precise, as though the shells knew where we would be. Stigler was correct. The shells did know. But he would not learn how or why until 1946, when American technical intelligence officers explained proximity fuse technology to captured German scientists. The revelation would shake German military confidence, even in defeat. They had lost not just to superior numbers or industrial capacity, but to a fundamental technological breakthrough their intelligence services never detected, despite 2.5 years of deployment. This is the story of the most successful secret of World War II, a weapon so effective that it remained classified even after Japan's surrender, and so misunderstood that German commanders blamed poor pilot training, declining fuel quality, and divine intervention, before they considered the possibility that American shells had simply become far more lethal than physics should allow. To understand why proximity fuses represented such a paradigm shift, one must first comprehend the limitations of anti-aircraft warfare as it existed through 1943. Since the First World War, the fundamental problem of aerial defense had remained unchanged. How does one hit a target moving at 300 miles per hour at altitudes ranging from 5,000 to 20,000 feet when one's projectile requires 4 to 7 seconds to reach intercept altitude? The mathematics were brutal and unforgiving. Traditional anti-aircraft doctrine relied on mechanical time fuses, descendants of artillery technology dating to the 1860s. Before firing, a gunner set the fuse to detonate after a calculated number of seconds. The calculation required accurate range finding, altitude estimation, and prediction of the target's future position. The gunner essentially fired at where the aircraft would be, not where it was. If all calculations proved correct, the shell would explode near the aircraft, sending fragments through aluminum skin, fuel tanks, engines, or crew. If any calculation was wrong, the shell exploded harmlessly in empty air, or worse, failed to explode at all. The U.S. Army's official 1942 gunnery manual acknowledged the difficulty frankly. Effective anti-aircraft fire requires the convergence of multiple simultaneous factors: accurate range finding, correct altitude estimation, proper lead calculation, reliable fuse setting, and consistent shell performance. The absence of any single factor results in complete failure. Studies conducted at Ardennes Proving Ground in Maryland demonstrated that experienced gun crews firing under ideal conditions required an average of 2,500 rounds to achieve one aircraft kill using mechanical time fuses. Under combat conditions, with aircraft taking evasive action, that figure rose to 5,000 rounds or more. The problem was geometrical. A typical high-explosive anti-aircraft shell created a lethal fragment pattern extending approximately 30 feet from the detonation point. An aircraft traveling at 300 miles per hour, or 440 feet per second, crossed that lethal zone in less than 1/10 of a second. If the fuse was set even half a second incorrectly, the shell would explode 220 feet from the aircraft, far beyond lethal range. The aircraft flew through empty air while deadly fragments dispersed uselessly in all directions. German doctrine, similar to American practice before 1943, emphasized volume of fire over precision. The 88mm flak gun, Germany's premier anti-aircraft weapon, achieved its reputation not through accuracy, but through sustained barrage fire. A typical flak battery of 4 guns could fire 80 shells per minute, creating a steel curtain through which aircraft had to fly. The strategy was statistical: fire enough shells and eventually one would detonate close enough to damage an aircraft. But this required enormous ammunition expenditure, extensive crew training, and elaborate fire control systems. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The British, under constant Luftwaffe bombardment from 1940 through 1942, developed the most sophisticated mechanical anti-aircraft systems. The Mark 7 Predictor, a mechanical computer weighing 3 tons, calculated firing solutions by tracking aircraft position through linked rangefinders and height-finding equipment. Operators fed in aircraft altitude, speed, and direction. The predictor output fuse settings and gun elevation angles, updated continuously. It was magnificent engineering, the pinnacle of mechanical calculation. It was also insufficient. British studies from the Battle of Britain indicated their defences required an average of 4,000 rounds per aircraft destroyed. The Americans, entering the war with limited anti-aircraft experience, initially adopted British systems and doctrine. The 90mm M1 gun, America's primary heavy anti-aircraft weapon, paired with the M9 Director, an electrical fire control computer developed at Bell Laboratories. The M9 represented advanced technology for its era, using servo motors and electrical circuits to calculate firing solutions. But it still relied on mechanical time fuses, still required shells to explode at precisely calculated moments, still suffered from the fundamental limitation that shells exploded based on time elapsed rather than distance from target. Naval anti-aircraft warfare faced even greater challenges. Ships moved, introducing additional variables into already complex calculations. Target aircraft changed altitude and direction constantly. Range finding at sea proved more difficult than on stable land. Yet the threat was existential. Japanese kamikaze tactics, introduced in 1944, meant that even damaged aircraft could strike their targets. A bomber or torpedo plane might absorb dozens of shell fragments and still complete its attack run. Only immediate catastrophic damage stopped such attacks, requiring shell bursts within immediate proximity of the aircraft. This was the state of anti-aircraft warfare when American scientists began exploring an entirely different approach. Not better mechanical computers or more powerful guns or larger warheads, but a fuse that didn't measure time at all. A fuse that measured distance and detonated only when close enough to guarantee destruction. The Germans, watching their aircraft losses climb throughout 1944, never conceived such technology was possible. They looked for conventional explanations, better training for American gun crews, perhaps improved range-finding equipment, or simply the overwhelming industrial capacity that produced more ammunition than German forces had ever faced. The truth was far more revolutionary and far more devastating. The proximity fuse's origins lay not in military research, but in pure scientific curiosity about radio wave behavior. In 1940, as the Battle of Britain raged and America debated intervention, a team at the Carnegie Institution's Department of Terrestrial Magnetism in Washington began investigating whether radio waves could reliably measure distance to moving objects. The concept was theoretically sound. Broadcast a radio signal, measure how long the echo takes to return, calculate distance from that time delay. Radar operated on this principle, but radar required elaborate ground stations with substantial power supplies and large antenna arrays. The challenge was miniaturization. Could radio distance measurement be compressed into an artillery shell? Such a shell would experience 20,000 times the force of gravity during firing, would spin at 30,000 revolutions per minute, would operate in temperatures ranging from -50 to +70 degrees Celsius, and would need to function flawlessly after being shipped across oceans, stored in field depots, and handled by crews wearing heavy gloves in combat conditions. Most scientists considered the requirements impossible. Section T, as the Carnegie Research Group was designated after reorganization under the National Defense Research Committee, approached the problem through systematic elimination of impossibilities. They began with vacuum tubes, the only electronic components available in 1940 capable of high-frequency radio operation. Standard vacuum tubes would shatter under artillery acceleration. Section T developed ruggedized tubes with reinforced filaments, shock-mounted elements, and glass envelopes strong enough to survive gunfiring. By June 1941, they had vacuum tubes that could survive 20,000 gravities. The first impossible requirement had been met. Power supply posed the next challenge. A radio transmitter requires electrical power. Batteries heavy enough to survive artillery firing would be too massive for practical shells. Section T engineer Ralph Baldwin proposed an elegant solution. Use the shell's rotation to drive a small generator. As the shell spins through the air, a tiny turbine on the fuse nose rotates at high speed, generating sufficient electrical power to operate the radio circuit. The generator had to begin operating within milliseconds of the shell leaving the gun barrel, had to function reliably at altitudes where air pressure was 1/3 of sea level, and had to operate continuously during the shell's entire flight time of 10 to 15 seconds. By December 1941, Section T had developed functioning prototypes. Laboratory tests demonstrated the fuse could detect objects at distances up to 100 feet and trigger detonation reliably. But laboratory conditions differed vastly from combat. The fuse needed to distinguish between legitimate targets and ground return, ignore rain and clouds, function reliably, despite radio interference from multiple shells fired simultaneously, and avoid premature detonation from friendly aircraft or ships. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from. Today, the operational breakthrough came in August 1942 during tests aboard the USS Cleveland off the Virginia coast. Test firings against radio-controlled target drones achieved hit rates 6 times higher than mechanical time fuses. The Navy immediately classified the results as secret and began crash production. By January 1943, proximity-fused shells were being issued to Pacific Fleet ships, with strict orders. Use only over water where duds could not fall into enemy hands. Never fire proximity-fused shells over land where the enemy might recover an intact specimen. The security measures were extraordinary. Proximity fuses were designated Mark 53 and Mark 54, generic designations that revealed nothing about their function. They were shipped in sealed containers, issued only to specific gun crews, and never stored near front lines where capture was possible. Gun crews received minimal information. They were told the new fuses improved accuracy, but nothing about how. Technical manuals listed them simply as fuse, mechanical, anti-aircraft, despite containing no mechanical timing mechanism whatsoever. This security obsession was justified. If German or Japanese scientists obtained an intact proximity fuse, they could potentially reverse engineer the technology. More immediately, they could develop countermeasures. Radio jamming might render the fuses ineffective. Metallized chaff, already used to confuse radar, might trigger premature detonation. Even simply knowing such fuses existed would alert enemy intelligence to investigate unusual anti-aircraft effectiveness and search for explanations. The Army initially resisted proximity fuse deployment for land-based anti-aircraft guns. Overland use risked duds falling into enemy hands. But by December 1944, with the Ardennes offensive threatening Allied lines and Luftwaffe activity intensifying, the restriction was lifted. 90mm anti-aircraft battalions received proximity-fused ammunition with orders to fire over Allied-controlled territory only and to recover any duds immediately. Sergeant Robert Pearson's gun crew at Malmedy was among the first land-based units issued the new ammunition. German intelligence had noted increased Allied anti-aircraft effectiveness, beginning in mid-1943, but attributed it to improved gunnery training, better fire control computers, or simply the overwhelming number of guns deployed. Luftwaffe reconnaissance photographed American and British anti-aircraft positions extensively, but saw nothing unusual. The 90mm guns looked identical whether firing mechanical or proximity-fused shells. The shells themselves appeared conventional in external appearance. The secret was inside, in components so small and sophisticated that even physical examination of fragments provided little insight into their function. This was the reality that confronted German aircrews in the war's final 18 months. They faced anti-aircraft fire that seemed to have become far more lethal without any visible change in enemy capabilities. Pilots reported shells bursting with uncanny accuracy, as though American gunners could predict evasive maneuvers. Flight surgeons documented increasing psychological stress among surviving aircrew. Veteran pilots described a new quality to Allied anti-aircraft fire, a precision that seemed to violate the laws of probability. They were correct, but the explanation lay in physics they couldn't see, delivered by technology they didn't know existed, achieving results their intelligence services couldn't explain. The Mark 53 proximity fuse, formerly designated VT fuse by 1943, contained technological sophistication that compressed years of radio development into a package 3 inches tall and 2 inches in diameter. The fuse screwed into the nose of a 90mm high-explosive shell, replacing the mechanical time fuse that had been standard since the First World War. Inside its aluminum casing, 4 miniature vacuum tubes, resistors, capacitors, and a transmitter-receiver circuit operated as a complete radio system smaller than a coffee cup. The transmitter broadcast at approximately 180 MHz, a frequency chosen because it reflected well from metal aircraft surfaces, but passed through clouds, rain, and atmospheric moisture without significant interference. The broadcast power was minimal, roughly equivalent to a small flashlight battery, but sufficient for the fuse's purpose. As the shell flew toward its target, The fuse continuously transmitted radio pulses and listened for echoes. When the echo strength indicated the shell had closed to approximately 70 feet from a solid object, the fuse triggered a detonating capacitor, which fired the shell's main explosive charge. The engineering challenges Section T overcame to achieve this functionality bordered on the miraculous by 1940 standards. The vacuum tubes had to survive acceleration forces that would crush ordinary radio tubes to powder. The filaments inside each tube were wound from wire 1/1000th of an inch in diameter, reinforced with special alloys, and mounted in shock-absorbing ceramic holders. The glass envelopes were thicker than standard radio tubes, yet had to maintain precise internal vacuum. Each tube was individually tested to destruction, with only those surviving simulated artillery firing being approved for production. The power supply was equally ingenious. As the shell left the gun barrel, spinning at 30,000 revolutions per minute, a small propeller-like turbine on the fuse nose began rotating. This turbine drove a miniature generator that produced sufficient electrical current to power the radio circuit. The generator had to begin operating within the first 20 feet of the shell's flight before the shell had travelled far enough to miss its target entirely. It had to continue operating throughout the shell's flight time, typically 12 to 15 seconds, while the shell climbed to altitudes of 15,000 feet or higher, where air pressure dropped to half of sea level. The fuse assembly required precision manufacturing beyond anything attempted in mass production. Each vacuum tube was individually calibrated. The transmitter circuit was hand-tuned to exact frequency. The detonating capacitor was tested for reliable discharge. A complete fuse contained approximately 50 individual components, each manufactured to tolerances measured in thousandths of an inch. Yet by late 1943, American factories were producing proximity fuses at rates exceeding 100,000 per month, each fuse costing approximately $18 to manufacture, roughly twice the cost of a mechanical time fuse, but requiring no setting or adjustment by the gun crew. The 90mm M1 anti-aircraft gun that fired these revolutionary fuses was itself a sophisticated weapon system. The gun weighed nearly 19,000 pounds in firing position, fired a 24-pound projectile at a muzzle velocity of 2,700 feet per second, and could engage targets at altitudes up to 30,000 feet. Each gun served by a crew of 8 men, the gun commander, 2 loaders, the fuse setter, whose job became obsolete with proximity fuses, the rammer, and 3 ammunition handlers. A well-trained crew could fire 25 rounds per minute under ideal conditions, though sustained combat rates averaged 15 rounds per minute. The M9 Director, the fire control computer that calculated firing solutions for the gun, was a marvel of electromechanical engineering. Developed at Bell Telephone Laboratories, it weighed 5,000 pounds and contained over 1,000 electrical relays, servo motors, and calculating mechanisms. Operators fed in target information, aircraft altitude from height-finding radar, range from optical rangefinders, and observed aircraft speed and direction. The M9 calculated the future position where shell and aircraft would meet, then transmitted elevation and azimuth angles electrically to the gun mount, which automatically pointed to the calculated position. With mechanical time fuses, the M9 also calculated and set the fuse timing. The fuse setter, working from director output, physically adjusted each fuse to the calculated detonation time before the shell was loaded. This required precise coordination and added seconds to each firing cycle. With proximity fuses, the fuse setting step disappeared entirely. The loader simply loaded the round, the rammer seated it, and the gun fired. The fuse would automatically detonate at optimal distance from the target, regardless of exact range or altitude. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The contrast in effectiveness was dramatic and immediate. Army anti-aircraft artillery effectiveness reports from the European Theatre of Operations documented the change with statistical precision. In the 6 months before proximity fuse deployment, 90mm gun battalions fired an average of 4,800 rounds per confirmed aircraft destroyed. In the first 3 months after receiving proximity-fused ammunition, that figure dropped to 900 rounds per aircraft destroyed. The improvement factor was not marginal. It was a fundamental transformation in weapon lethality. Guns that had been marginally effective became devastatingly lethal. But the statistics only captured part of the reality. Gun crews noticed the difference immediately in ways that numbers couldn't fully express. Sergeant William Morrison, serving with the 796th Anti-Aircraft Artillery Battalion in France, wrote to his family in February 1945, describing the new ammunition in carefully vague terms to avoid censorship. "We received improved shells last month. The results have been extraordinary. Aircraft that previously would have escaped now fall from the sky with regularity. The boys say our guns have become twice as effective, though personally I believe that's conservative. Morale has improved tremendously. We finally feel we're making a real contribution to the air battle." The Luftwaffe first encountered proximity-fuzzed anti-aircraft fire in significant numbers during Operation Bodenplatte, the massive German air offensive launched on January 1, 1945. The operation was Hitler's desperate attempt to destroy Allied air power on the ground, striking forward airfields in Belgium, the Netherlands, and France at dawn, with nearly 900 aircraft, the largest Luftwaffe mission since 1943. The plan relied on surprise and overwhelming numbers. What German planners couldn't account for was the recent deployment of proximity-fused ammunition to Allied anti-aircraft batteries, protecting those same airfields. Oberleutnant Heinz Nock, a Luftwaffe fighter pilot with 33 confirmed victories, participated in the attack on Volkel airfield in the Netherlands. His post-war memoir, I Flew for the Führer, described the mission with bitter clarity. "We approached at minimum altitude, expecting to catch the enemy unprepared. Instead, we flew into defensive fire of unprecedented accuracy. The flak bursts seemed to anticipate our every movement. Aircraft exploded around me in rapid succession. I saw Lieutenant Hartmann's Fokker-Wulf disintegrate in a single explosion. Feldwebel Kruger's Messerschmitt fell burning with no chance for the pilot to bail out. In less than 2 minutes, my group lost 7 aircraft to ground fire. This was not the scattered, ineffective flak we had grown accustomed to. This was something entirely different." Nock survived Bodenplatte but lost his Bodenplatte entire squadron within 3 weeks. Of the 24 pilots who began January 1945, only 4 remained operational by month's end. Nock attributed the losses to new American anti-aircraft methods, never suspecting that the shells themselves had fundamentally changed. His combat reports, preserved in Luftwaffe archives, repeatedly describe anti-aircraft fire as impossibly accurate and appearing to track individual aircraft. These reports reached Luftwaffe intelligence headquarters in Berlin, where analysts struggled to explain the pattern. German intelligence reports from January 1945 show the confusion clearly. One report, declassified in 1973, stated, "Enemy anti-aircraft effectiveness has increased dramatically in recent weeks. Possible explanations include improved optical range finding, increased ammunition expenditure, better crew training, or deployment of new radar-based fire control systems. Recommend increased reconnaissance of enemy anti-aircraft positions and interrogation of captured enemy gun crews." The report considered every conventional explanation except the correct one, that American shells no longer relied on timed detonation at all. The Navy had experienced proximity fuse effectiveness earlier, during the Pacific Island campaigns of 1944. Japanese kamikaze attacks provided the clearest test of the weapon's capability. Traditional anti-aircraft fire often damaged kamikaze aircraft without stopping them. A bomber could lose an engine, suffer structural damage, and still complete its dive into a ship. Only immediate catastrophic damage stopped kamikaze attacks. Proximity fuses delivered exactly that. The USS Hugh W. Hadley, a Fletcher-class destroyer, demonstrated the technology's life-saving potential during radar picket duty off Okinawa on May 11, 1945. The ship faced coordinated attacks by over 150 Japanese aircraft in a 90-minute period. The Hadley's 5-inch guns, firing proximity-fused shells exclusively, destroyed 23 attacking aircraft. The ship's action report, written by Commander Baron J. Mullaney, documented the Fuze's effectiveness. The new ammunition proved devastatingly effective. Aircraft approaching within range were destroyed with remarkable consistency. Gun crews reported that targets appeared to explode upon entering effective range, often before visual fire control could establish precise aim. Without this ammunition, the ship would certainly have been lost. The Hadley was eventually hit by kamikaze strikes and severely damaged, but survived because the Fuzes had destroyed enough attackers to prevent overwhelming damage. The ship's survival was credited directly to proximity-fused ammunition. Navy statistics from the Okinawa campaign showed that ships equipped with proximity Fuzes survived kamikaze attacks at 3 times the rate of ships using only mechanical fuses. German prisoners of war, interrogated about anti-aircraft effectiveness, provided consistent testimony. They had noticed increased Allied anti-aircraft accuracy beginning in mid-1943, but had no explanation. Hauptmann Werner Hoffmann, a Junkers Ju-88 bomber pilot shot down in March 1945, described the experience during interrogation. The flak bursts seemed to follow our aircraft. We would take evasive action, diving or climbing, and the explosions would appear at our new altitude. It was as though the shells knew where we were going. Several pilots reported the same phenomenon. We assumed the Americans had developed some new form of radar-linked gunnery, but we saw no evidence of additional equipment at their gun positions. The psychological impact on German aircrew was severe and measurable. Luftwaffe medical records from 1945 show dramatic increases in combat stress casualties among fighter and bomber pilots. Flight surgeons reported pilots refusing to fly missions over heavily defended areas, citing suicidal flak concentrations. Pilots with excellent combat records began exhibiting symptoms of severe anxiety before missions. Some requested transfer to less dangerous assignments. Others developed physical symptoms, tremors, insomnia, that disqualified them from flight duty. The Luftwaffe's training command struggled to explain the losses to new pilots. Instructors emphasized evasive maneuvers, altitude changes, and speed variation to avoid anti-aircraft fire. But these traditional tactics proved ineffective against proximity fuzzes. An aircraft diving to evade a predicted shell burst would find the shell detonating at its new altitude. A pilot climbing rapidly would encounter explosions at the higher elevation. The fundamental assumption that shells exploded at predetermined times and altitudes no longer applied. German pilots were trying to evade weapons that operated on principles they didn't understand and couldn't counter. By March 1945, German technical intelligence had accumulated substantial evidence that Allied anti-aircraft capability had fundamentally changed, yet they remained unable to identify the cause. Luftwaffe loss reports showed a clear pattern. Aircraft destroyed by anti-aircraft fire had increased from 12% of total losses in 1943 to 28% in the first quarter of 1945, despite the Luftwaffe flying fewer missions and facing fewer total anti-aircraft guns than earlier in the war. The increased lethality was undeniable, but explanations remained speculative. General-Lieutenant Josef Schmid, commander of I Jad Corps, ordered a comprehensive study of anti-aircraft losses in February 1945. The resulting report, captured by American forces and translated in 1946, documented the German military's confusion in detail. Enemy anti-aircraft fire has become markedly more effective since mid-1944. Analysis of pilot reports indicates that flak bursts occur with unusual proximity to our aircraft, often within lethal fragmentation range, even when aircraft execute violent, evasive maneuvers. Several explanations have been proposed. First, that enemy gun crews have achieved unprecedented training levels. This seems unlikely given the large number of replacement crews observed. Second, that enemy fire control systems have been improved with advanced radar integration. This is possible, but photographic reconnaissance shows no significant changes to enemy anti-aircraft installations. Third, that enemy ammunition expenditure has increased substantially, creating denser barrage patterns. Ammunition consumption data does not support this hypothesis. The cause of increased enemy effectiveness remains unknown. The report recommended several countermeasures, all based on conventional assumptions about anti-aircraft warfare. Increased altitude for bomber formations, more radical evasive maneuvers, attacks coordinated to overwhelm defensive fire, and fighter escorts specifically tasked with suppressing anti-aircraft positions. None of these measures proved effective because they addressed a threat that didn't exist. German commanders were preparing for improved versions of weapons they already understood, not for a fundamental technological breakthrough they couldn't imagine. German intelligence did make one crucial observation, though they failed to grasp its significance. Several pilots reported that American anti-aircraft shells appeared to detonate even when no aircraft was near the burst point, creating patterns of explosions that seemed random and wasteful. These pilots had actually observed proximity fuses detonating from ground return, the radio echo from terrain below the shell's flight path. The fuses were designed to ignore ground return under most circumstances, but occasionally terrain features or specific angles caused premature detonation. German analysts interpreted these observations as evidence of poor American gunnery or defective ammunition, never considering that the shells might be detonating based on proximity to the ground rather than preset timing. The closest the Germans came to discovering proximity fuses occurred in January 1945, when Luftwaffe ordnance specialists examined fragments from anti-aircraft shells that had damaged aircraft but not destroyed them. The specialists noted unusual components in some fragments, small metal pieces with fine wire attachments that resembled radio equipment. A technical report speculated these might be components of a new type of fuse mechanism, possibly radio-based. The report was filed and apparently never reached higher command levels. Even if it had, German scientists would have faced significant challenges reverse engineering the technology from fragments alone. American security measures continued to prevent intact fuses from falling into enemy hands. Dud proximity-fused shells, which occasionally failed to detonate, were recovered immediately by specially designated ordnance disposal teams. These teams operated under standing orders to recover duds before enemy forces could reach the area. In several cases, American infantry units were ordered to hold positions specifically to prevent German forces from accessing areas where proximity-fused duds had fallen. The security effort succeeded. Throughout the European War, German forces never recovered an intact proximity fuse for technical analysis. The security extended beyond physical recovery. Censorship prevented American soldiers from writing detailed descriptions of the new fuses in letters home. Technical manuals classified proximity fuses as secret and restricted access to essential personnel only. Gun crews were briefed on the fuses' improved effectiveness, but not on their operating principles. Even ordnance officers responsible for ammunition supply were told only that the new fuses required no setting and should be used preferentially against aircraft targets. The goal was to prevent even vague descriptions from reaching enemy intelligence through captured documents or prisoners of war. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. This compartmentalization of information proved remarkably effective. When American soldiers were captured, they could describe proximity-fused ammunition only in general terms. New shells that work better, improved fuses that don't require setting, ammunition that's more accurate. These descriptions, while true, provided no actionable intelligence to German interrogators. The technical principles remained completely obscured. German intelligence collected hundreds of such reports, but could extract no useful technical information from them. The statistical reality of proximity fuse effectiveness became clear only through comprehensive post-war analysis. The U.S. Strategic Bombing Survey, conducted in 1945 and 1946, compiled extensive data on anti-aircraft effectiveness throughout the war. The survey's anti-aircraft section documented that proximity-fused ammunition increased the probability of kill per round, fired by a factor of approximately 3 to 5 times compared to mechanical time fuses, depending on target type and engagement conditions. For naval applications, where ship's movement complicated fire control, the improvement factor reached 7 to 1 in some circumstances. The survey also documented ammunition savings. Despite firing significantly fewer total rounds in 1945 than in 1944, Allied anti-aircraft units achieved substantially more aircraft kills. The proximity fuse's efficiency meant that gun crews could engage targets with smaller ammunition expenditures while achieving higher success rates. This efficiency freed up ammunition for other uses and reduced the logistical burden of supplying anti-aircraft units, an often overlooked benefit of the technology. Perhaps most significantly, the proximity fuse's psychological impact on Allied gun crews proved as valuable as its technical effectiveness. Knowing that their weapons had become dramatically more lethal, improved morale and combat effectiveness in ways that transcended mere statistics. Gun crews fired with confidence, knowing that each round had a realistic chance of destroying its target. This confidence translated into steadier aim, more disciplined fire control, and better overall performance. The proximity fuse transformed anti-aircraft gunnery from an exercise in statistical probability to a weapon system that crews could trust to protect them and their comrades. The truth reached German military and scientific personnel in stages during the spring and summer of 1946, as American technical intelligence teams systematically briefed captured German scientists and officers on Allied technological developments. The proximity fuse briefings, held at various detention facilities including Ashcan in Luxembourg and Dustbin in Frankfurt, produced reactions ranging from disbelief to profound dismay. German scientists who had worked on similar concepts realized how far behind their own research had fallen. Military officers understood that they had been fighting an enemy with capabilities they never suspected existed. General Engineer Erich Schneider, who had directed Luftwaffe technical development from 1943 to 1945, attended one of these briefings at Dustbin facility in June 1946. His reaction, recorded by American intelligence officers, captured the shock of revelation. When the American officer explained the proximity fuse's operating principle, I initially thought he was exaggerating or perhaps even mocking us. Radio components inside an artillery shell? Miniature vacuum tubes surviving gun firing? It seemed impossible. But when he showed us actual fuse components, explained the engineering solutions, and presented effectiveness statistics, I realized we had been completely outmaneuvered technologically. We had known American anti-aircraft fire had become more effective. We attributed it to better training, more guns, improved fire control. We never imagined they had fundamentally changed how the shells themselves operated. German scientists had actually explored proximity fuse concepts earlier in the war. In 1940, researchers at Rheinmetall Borsig began investigating photoelectric fuses that would detonate when an aircraft's shadow crossed a light sensor. The concept showed promise in laboratory tests but proved impractical for field use. The photoelectric cells were too fragile, required perfect weather conditions, and couldn't distinguish between aircraft and clouds. The project was abandoned in 1941. German researchers also briefly examined radio-based proximity detection, but concluded that vacuum tubes couldn't survive artillery acceleration and that power supply problems were insurmountable. These were precisely the challenges Section T had overcome through systematic engineering development. The revelation that American scientists had solved these problems produced a cascade of second-order realizations among German technical personnel. If American industry could mass-produce components as sophisticated as proximity fuses, incorporating miniature vacuum tubes, precision generators, and complex electrical circuits, then American industrial capability exceeded German estimates by even wider margins than previously understood. The proximity fuse wasn't just a clever weapon. It was evidence of industrial and technical capacity that Germany could never have matched even under optimal circumstances. Dr. Herbert Wagner, who had developed the HS-293 guided anti-ship missile for the Luftwaffe, examined proximity fuse components in detail during his debriefing. His technical assessment, preserved in American intelligence files, acknowledged the achievement with professional respect. The miniaturization alone is remarkable. The vacuum tubes are masterpieces of engineering, smaller and more robust than anything we achieved. The power generation system is elegant in its simplicity. The radio circuit is sophisticated yet manufacturable. But most impressive is that the Americans produced these in quantities of millions while fighting a global war. This is not laboratory science. This is industrial engineering at a level we never approached. When I consider that each Fuze required hand calibration of multiple components, yet they manufactured them at rates exceeding 100,000 monthly, I begin to understand how thoroughly we underestimated American industrial capacity. The proximity fuse's security throughout the war represented another aspect of American capability that impressed German intelligence officers. Oberst Friedrich Wilhelm von Mellenthin, a senior intelligence officer who had analyzed Allied capabilities throughout the war, learned of proximity fuses during his interrogation in May 1946. His response highlighted the intelligence failure. We collected reports of improved American anti-aircraft effectiveness beginning in mid-1943. We analyzed hundreds of pilot reports, examined battle damage, studied captured American equipment and documents. Yet we never detected the proximity fuse's existence. This represents a comprehensive failure of German intelligence. Either American security measures were extraordinarily effective, or our intelligence capabilities had deteriorated beyond our own recognition. Probably both. The statistical comparisons presented during these briefings made the technology's impact undeniable. American officers showed German personnel charts comparing anti-aircraft effectiveness before and after proximity fuse deployment. The graphs showed sharp discontinuities in rounds per kill ratios, aircraft loss rates, and mission success rates. The data was irrefutable. German losses to anti-aircraft fire had increased not because Allied gunners had become better trained or because more guns were deployed, but because the fundamental lethality of each gun had increased by factors of 3 to 5. For Luftwaffe pilots held in prisoner of war camps, learning about proximity fuses provided bitter vindication. The unusual accuracy they had reported, the seemingly impossible flak bursts, the feeling that shells were tracking their movements, all had been real. Oberleutnant Franz Stigler, whose combat report after the December 16th engagement at Malmedy had described American fire as impossibly precise, learned the explanation in July 1946. His recorded response: "I feel simultaneously relieved and angry. Relieved that my observations were correct, that I wasn't losing my mind or my nerve. Angry that we were sent against such weapons with no warning, no understanding of what we faced. Had we known the Americans possessed such technology, we might have developed different tactics, though I doubt even different tactics would have helped much. You cannot evade a shell that detonates when it gets close to you. There is no counter-tactic to that except not flying at all. The proximity fuse's success in World War II obscured its development costs, both financial and human. The National Defense Research Committee spent approximately $29 million developing proximity fuse technology between 1940 and 1945, equivalent to roughly $450 million in 2023 currency. This represented one of the war's largest single weapons development programs, comparable to the early costs of the Manhattan Project, before atomic bomb development accelerated in 1944. Section T's research facility at the Applied Physics Laboratory, established at Johns Hopkins University in 1942, specifically for proximity fuse development, employed over 700 scientists and engineers at its peak. These highly trained personnel were diverted from other war work, from radar development, from communications research, from a dozen other critical projects. The decision to concentrate such resources on a single weapon system represented a calculated gamble by American military planners. The gamble paid off. but it might easily have failed if any of dozens of technical challenges had proven insurmountable. Production of proximity fuses consumed substantial industrial resources. By war's end, American factories had produced over 22 million proximity fuses of all types, including variants for 5-inch naval guns, 90mm anti-aircraft guns, and even artillery shells. Each fuse required vacuum tubes, precision components, and careful assembly that demanded skilled labor and sophisticated manufacturing equipment. The Crosley Corporation in Cincinnati converted its radio manufacturing facility to produce proximity fuses, eventually delivering over 5 million units. RCA, Sylvania, Raytheon, and Eastman Kodak all produced components or complete fuses, representing a significant allocation of America's electronic manufacturing capacity. The human cost of proximity fuse development rarely appears in histories of the weapon. At least 12 scientists and engineers died in accidents during development and testing, several from premature detonations during fuse testing, others from aircraft crashes during live fire tests. Navy personnel conducting shipboard tests faced additional risks. The destroyer USS Aaron Ward suffered casualties during proximity fuse testing when a defective round detonated prematurely, killing 2 sailors and wounding 5 others. These deaths occurred far from combat, in pursuit of a weapon whose effectiveness wouldn't be fully demonstrated until months or years later. The proximity fuse also imposed costs on Allied tactical operations that are seldom acknowledged. The security restrictions meant that fuses couldn't be used in situations where duds might fall into enemy hands. This prevented their use in close air support missions, where shells fired at low-flying aircraft would fall in contested territory. It prevented their use in many tactical situations where they would have been most valuable. Gun crews sometimes had to choose between using proximity fuses with their superior effectiveness but restricted circumstances, or mechanical fuses with lower effectiveness but no restriction on where they could be employed. The restriction on overland use until December 1944 meant that proximity fuses weren't available for some of the war's most critical anti-aircraft battles. During the Schweinfurt-Regensburg raids in August 1943, when American bomber formations suffered catastrophic losses to German fighters, the proximity fuses that might have protected them were restricted to naval use only. During Operation Market Garden in September 1944, when German aircraft attacked Allied airborne drops, proximity fuses remained forbidden for land-based anti-aircraft guns. These restrictions, while necessary for security, meant accepting higher losses in specific battles to preserve the weapon's secrecy for the war's remainder. The psychological costs on German military personnel, learning post-war that they had faced such technology unknowingly, represented another hidden toll. Many former Luftwaffe personnel experienced feelings of betrayal, not by their own command necessarily, but by circumstance. They had flown missions against increasingly lethal defenses, while their intelligence services assured them that Allied capabilities were understood and countered. The revelation that a fundamental technology had been deployed against them for 2 years without their knowledge undermined confidence in their entire war experience. If they had missed something so significant, what else had they failed to understand? Hauptmann Werner Hoffmann, the Ju-88 pilot who had described flak bursts following his aircraft during interrogation, later wrote about learning of proximity fuses. I felt like I had been fighting blind. Every briefing assured us we understood Allied capabilities. Every intelligence report claimed we knew their weapons and could counter them. But we were flying against weapons we didn't know existed, that worked on principles we hadn't imagined. This wasn't just a technological gap, it was a fundamental failure of understanding. It makes me question everything I thought I knew about the war. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The proximity fuse's effectiveness also created a feedback loop that increased Luftwaffe losses in ways beyond direct anti-aircraft kills. As anti-aircraft fire became more lethal, German pilots flew higher to avoid it, which made them more visible to Allied fighters and reduced their own effectiveness against ground targets. When they flew lower to evade Allied fighters, they encountered devastating anti-aircraft fire. The proximity fuse created a tactical dilemma with no good solution. German pilots in the war's final months found themselves trapped between increasingly effective air defenses and overwhelming Allied fighter superiority, with each threat pushing them into greater danger from the other. The weapon's success also influenced post-war military development in ways that imposed long-term costs. The proximity fuse demonstrated that sophisticated electronics could be militarized successfully, which accelerated the electronics arms race of the Cold War. Nations invested billions in developing electronic warfare capabilities, radar systems, guided weapons, and countermeasures. The proximity fuse showed that victory in modern warfare required not just brave soldiers and strong industry, but technological superiority in areas most citizens would never see or understand. This realization shaped military planning for the next 70 years and continues to influence defense policy in the 21st century. The proximity fuse's influence extended far beyond World War II anti-aircraft warfare, reshaping military technology and doctrine for generations. The weapon represented a fundamental shift in how weapons functioned, from mechanical systems that operated on preset parameters to electronic systems that responded dynamically to their environment. This shift foreshadowed the electronic revolution in military technology that would dominate the latter half of the 20th century. By the Korean War, proximity Fuzes had become standard for American anti-aircraft and artillery ammunition. During the Chinese intervention in November 1950, proximity-fused artillery shells proved devastatingly effective against massed infantry attacks. Shells bursting above ground at optimal height created fragment patterns far more lethal than ground-burst explosions. A single proximity-fused 105mm artillery shell could create casualties across an area 5 times larger than a mechanically fused shell. Chinese commanders, like their German predecessors, initially struggled to understand why American artillery had become so lethal. The technology evolved rapidly after World War II. Post-war proximity fuses became smaller, more reliable, and less expensive. The miniature vacuum tubes that had required careful hand assembly in 1943 were replaced by transistors in the 1950s, then by integrated circuits in the 1960s. Modern proximity fuses are solid-state electronic devices, mass-produced at costs far below their World War II equivalents while offering superior performance and reliability. Every major military in the world now employs proximity fuse technology in anti-aircraft missiles, artillery shells, and air-to-air missiles. The conceptual breakthrough the proximity fuse represented, that weapons could sense and respond to their environment, led directly to modern guided weapons. Today's missiles don't just fly toward a preset point. They track their targets, adjust their trajectories, and optimize their attack profiles. Modern air defense systems detect incoming threats, calculate optimal intercept points, and guide missiles to targets with precision. World War II engineers couldn't have imagined. All of this descended from Section T's realization that a shell could measure its own distance from a target and act on that information. The security aspect of the proximity fuse program also established important precedents. The successful compartmentalization of information, the effective prevention of enemy intelligence from detecting a widely deployed technology, became a model for subsequent classified weapons programs. The Manhattan Project applied similar security principles with even greater stringency. Cold War weapons development routinely employed compartmentalized information, restricted deployment, and elaborate counterintelligence measures directly derived from proximity fuse security procedures. For the German military and scientific establishment, proximity fuzzes represented a cautionary example, studied intensively in post-war years. The Bundeswehr, established in 1955, incorporated lessons from the proximity fuse experience into its intelligence and technical assessment procedures. German military doctrine emphasized the importance of understanding not just enemy equipment, but enemy technological capabilities and developmental trends. The assumption that enemies would employ only known technologies had proven disastrously wrong. Future planning would need to account for the possibility of fundamental technological breakthroughs. The individual stories of those who encountered proximity fuses firsthand concluded in varied ways. Technical Sergeant Robert Pearson, whose gun crew fired proximity-fused ammunition at Malmedy in December 1944, survived the Battle of the Bulge and returned to Indiana in October 1945. He worked as a machinist for 37 years, rarely discussing his war service. In a 1989 interview for a local history project, he briefly mentioned the improved ammunition his unit received. "We got new shells in December 44. They worked a lot better than the old ones, made a real difference. But we weren't allowed to talk about them at the time, and by the time the war ended, nobody seemed interested in anti-aircraft gunnery anymore. It was all about atomic bombs and jet aircraft by then." Oberleutnant Franz Stigler, the German pilot who survived the December 16th engagement and described American flak as impossibly precise, was captured in April 1945 and spent 18 months in a prisoner of war camp. He learned about proximity fuses during a technical briefing in late 1946. After repatriation, he worked as a commercial pilot for Lufthansa until retirement in 1975. In his memoirs, published in German in 1982, he devoted an entire chapter to proximity fuses, analyzing how their unknown presence had affected Luftwaffe tactics and morale. He concluded, "We were fighting a war where the enemy possessed capabilities we couldn't detect and couldn't counter. This is the nightmare scenario for any military force. The Americans achieved it through brilliant engineering and rigorous security. We lost not just because they had more aircraft and more pilots, but because their technology had leaped ahead in ways we never detected until too late." Dr. Merle Tuve, who directed Section T and oversaw proximity fuse development, received the Medal of Merit in 1946 for his contributions to the war effort. He returned to civilian scientific research, directing the Carnegie Institution's Department of Terrestrial Magnetism until 1966. In later interviews, he reflected on the proximity fuse program with mixed feelings. "We created a weapon that saved thousands of Allied lives, probably tens of thousands when you account for the ships that weren't sunk and the aircraft that successfully completed their missions. I'm proud of that. But I'm also aware that we accelerated the militarization of science and technology. The proximity fuse showed that fundamental breakthroughs could be weaponized rapidly if sufficient resources were applied. That lesson shaped Cold War military research in ways I'm not entirely comfortable with. We opened a door that perhaps should have remained closed." The statistical legacy of proximity fuses appears in military effectiveness studies to this day. The weapon is routinely cited as one of World War II's most cost-effective technological developments, delivering enormous tactical advantage relative to its development cost and production burden. Studies of military innovation frequently examine the proximity fuse program as a model of successful research translation, from laboratory concept to mass-produced weapon in under 3 years. The program demonstrated that focused research, adequate funding, and clear military requirements could produce revolutionary capabilities even during wartime's chaotic conditions. For historians of World War II, the proximity fuse represents a fascinating case study in technological surprise and intelligence failure. The Germans never detected the weapon despite losing thousands of aircraft to it. This intelligence failure, comparable to the Allied success in breaking Enigma codes, showed that technological superiority could be maintained through operational security even during widespread deployment. The lesson remains relevant in an era where military technology advances rapidly and technological surprise remains a potent strategic advantage. The proximity fuse also serves as a reminder that warfare's decisive factors often operate invisibly. Soldiers on both sides saw the same external reality: guns firing, shells exploding, aircraft falling. But the mechanisms producing those results had fundamentally changed in ways only one side understood. The German pilots who reported impossibly accurate flak were describing reality accurately. American shells had become impossibly accurate by previous standards. But impossibility had simply been redefined by technology the Germans didn't know existed. In the end, The proximity fuses story reveals how technological advantage shapes military outcomes not just through raw capability, but through the psychological and operational effects of fighting an enemy whose capabilities you don't fully understand. The Germans in 1944 and 1945 weren't just facing superior numbers and industrial capacity. They were facing weapons that operated on principles their intelligence services never detected and their tactical doctrine couldn't counter. That combination, material superiority plus conceptual surprise, proved devastating. The fountain pen that Technical Sergeant Robert Pearson used to write home from Belgium in December 1944 never mentioned proximity fuses directly, limited by censorship and security restrictions. But between the lines, in his descriptions of improved morale and increased effectiveness, the truth was visible to anyone who knew where to look. American anti-aircraft guns had become dramatically more lethal, not because gunners had become better trained or more numerous, but because the shells themselves had changed in ways the enemy would never suspect until long after the war ended. That secret, maintained successfully for 2.5 years of intensive combat, represented one of World War II's most complete intelligence victories and contributed directly to Allied air superiority in the war's final 18 months. The Germans never knew what killed so many of their aircraft. They were fighting blind against weapons they couldn't see, built on principles they hadn't imagined, produced by an industrial system they had catastrophically underestimated. The proximity fuse, small enough to hold in one hand, represented everything that had gone wrong with German intelligence, everything that had gone right with American technology, and everything that would shape military competition for the 70 years that followed. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.